take the complex plane, remove the 0 point, then the Galois action gives the reflection. And that's why in the R-motivic case, if we apply the C2 equivariant Betti realization, we get this circle with reflection, this C2 equivariant spectra, or actually the suspension of that, the suspension spectrum of that. And oops. In the third case, an R-motivic Allenberg-MacLean spectra associated to the event group A is realized to the corresponding C2 equivariant Allenberg-MacLean spectra associated to the constant Mackey functor. So this is the constant Mackey functor. And the notation is A with the underline. Okay. And it may be helpful to write down their homotopy groups. So let me give an example here. In R-motivic or C-motivic, in the motivic case, since you can calculate the bigraded homotopy groups of things, because we have two circles, and these circles, they're bigraded, and the whole category is a symmetric monoidal category, so that we can smash these circles of different gradings together to get bigraded spheres in this category. And mapping out of these spheres give us bigraded homotopy groups in the motivic categories. And in the in the C2 equivariant category, things are also bigraded because we can grade everything over the representation range. And for C2, the irreducible, it has the trivial representation and it has a sign representation. These are the two irreducible representations for this group C2. So here we can also grade homotopy groups over these bigradings, these two gradings. And let me write down, for example, in the C2, in the C-motivic case, let me use this notation to denote that this is a bigraded C-motivic homotopy groups. In the C-motivic case, if I take the C-motivic Allenberg-MacLean spectrum associated to F2, this is F2, a joint polynomial generator tau, and tau is in degree 0, -1. So this is the C-motivic Allenberg-MacLean spectrum, the C-motivic coefficient ring of the Allenberg-MacLean spectrum. And the R-motivic one, it's a little bit complicated, more complicated than that, but it's still nice. So the formula is that the R-motivic coefficient ring for the Allenberg-MacLean spectrum associated to F2, it's a polynomial generator with, it's a polynomial algebra with two generators, tau and rho. And tau here is also in degree 0, -1, and rho here is in degree -1, -1. And C2 is a bit complicated. C2 is a bit complicated. If I take the Allenberg-MacLean spectrum associated to the constant Mackey factor F2 underline, this is, and take its coefficient ring. It has, well, let me change the notation. It's a polynomial algebra, well, additively a polynomial algebra plus something that is infinitely divisible. And here, the degree for U is 0, -1. The degree for A is -1, -1. Or a better way, maybe a better way to write that is, this is 1 minus sigma, and this is negative sigma. So sigma is a sign representation. Okay, and as you expected, under this map, the C2 realization map, tau is mapped to realized to U, and rho is realized to A. Okay, and people, well, sometimes people like to draw pictures for these polynomial, these coefficient rings. Armotypically, it's usually drawn like this. So this is negative, the first grading, which we call S. And this is the other grading, and rho is here, tau is here. And this is usually called the positive cone. This is armotypic, and C2 equivariantly. I have this positive cone. This is A, this is U, and something here. There's nothing in degree 0, 1. And this is usually called the negative cone. And the negative cone part, because of the multiplicative structure, it's usually harder to describe or harder to calculate. So this part is harder to. And one advantage of working in the R-motivic category instead of working in the C2 equivariant category is that in the R-motivic category, for example, in this example, you have a better description of the homotopy groups of Allenberg-MacLane. In R-motivic category, things are usually easier to calculate. And in the C2 equivariant category, you need to deal with an active cone, and which is hard, which is a bit harder. But there is actually a way to first do things in the R-motivic category and recover the C2 equivariant category. So this part is exactly the same, and most of the case, the negative cone part can be recovered from the positive cone information. For example, in Baron Shah's work, they show that you can use R-motivic calculation to get C2 equivariant result. So an example they use in their paper is that if you consider the Tate diagram, so the Tate diagram in the C2 equivariant category, that is, I have a C2 equivariant spectrum, I can form a square by taking what is called the geometric completion, the homotopy completion, the Tate completion, and this forms a pullback square. And these three corners, these three equivariant spectrum, they can be calculated by completing or inverting the element A. So the element A is this A, and it can also be left to an element in the C2 equivariant stable stems, for example. And the geometric completion here can be calculated by inverting A, and this can be calculated by complete at A, and this is complete and invert. Okay. And they show that you can use Baron-Shah showed that you can use this Tate diagram, and then you start from R motivic to get to the C2 equivariant. And we can test that on the case of F2, the Allenberg-MacLean spectra, HF2, the Allenberg-MacLean spectra. So how to do this is that you start with the R motivic calculation, this positive cone, and then you invert A, and in this case, while rho is mapped to A, so you invert rho, and you get the copy paste. You get the upper right corner, which is, oops, you invert rho. Yeah, so you get this. Okay. This is the upper right corner. And you complete at rho, and so here implicitly you need to invert tau. So this is what you'll get on the lower left corner. And the complete and invert is a whole plane. And you do a pullback diagram calculation that will give you this picture. That will give you, oops, not enough space. That will give you this picture. So this is an example of calculating C2 equivariant from R motivic. And now let's get back to this diagram. Let me duplicate it. So we see that we have this do R calculation first and use that to recover C2 calculation. And now our question is that, okay, if we don't want just C2 calculation, we want CP, then what is the analog of this R motivic category? So the question is there a CP analog of SHR? Or more precisely, we want to put CP here, and we want to find some question mark category here, such that we have an analogous diagram like this. Okay, so this is our question. And the advantage of having such a question mark is that this may help with the CP equivariant calculation, because we can do some similar process. We can potentially we can do easier calculation here and use it to recover calculation in the CP equivariant category. And the immediate thought to build this question mark category is that, okay, if we can find some motivic category, and that motivic category the realization of that has some Goa action of CP, then maybe we can build the square. But that's not doable, because if you think about the Goa action, the absolute Goa group, then you get C2 and the trivial group and or other reasonable things, they're profinite. So it's not, you cannot get CP for an odd prime P. That route doesn't work. So instead, our approach is that if we can understand in this square, if we can understand how to build the C-motivic stable homotopy category out of the stable homotopy category, or we can understand how to build the R-motivic stable homotopy category out of the C2 category, then maybe we can do something analogously. We start from the CP and using this analogous way to build this question mark. So approach, well, start from SHCP and try to build the question mark. And to do that, we need to understand how to go from here to here and here to here. And let's look at these two examples we have. So the step one from SH to, not step one, example one from SH to the C-motivic. So we have the theorem by Gilgay, Wang Xu. And they say that if you restrict to the cellular C-motivic category, then this is a deformation of SH with parameter. How? Yeah, let me make a note here. So everything starting from this point will be P completed. So the more precise statement of the theorem is that the P-completed cellular stable homotopy, C-motivic stable homotopy category is a deformation of the P-completed stable homotopy category with parameter tau. And just to simplify the notation, I'm not going to include this P completion in my writing, but everything is P complete. Okay.
Hana, excuse me, is it not without P completion? Is the theorem not true?
Sorry, it's hard to. Can you say that again?
Without the P completion, is the theorem not true?
No, they don't prove it without P completion. Yeah, yeah, you need to P completed. Okay, yeah. So first, I think maybe one thing is that you need to P completed to get this tau. This tau is an element. It can be realized as an element in. Let me write. It can be realized as an element in the C-motivic 0, -1 of the sphere after P completion. But without P completion, you don't have tau. So for example, this is one intuition why P completion is necessary.
Thank you.
Okay, yeah. Thanks for the question. So we have this theorem which tells us that one way to think about the C-motivic category, but just this, only the cellular part. So this is a cellular. The cellular part is that it can be thought of as a deformation. And from a calculational point of view, we have this description, and that means that we can compute C-motivic things using tau Box-Stein spectral sequence. So one computational tool out of this theorem is that we can think about the tau Box-Stein spectral sequence. And the tau Box-Stein the tau Box-Stein spectral sequence, it has the following form. So you start with the C-motivic homotopy groups of a C-motivic spectrum smash with C tau. And when you smash with C tau, you kill the element tau. And the E1 page is that adjoint the polynomial generator tau, and this should converges to the homotopy groups, this C-motivic homotopy groups of X. And right, this is co-fiber of tau. And another thing I can write down is that if you take X to be the sphere, to be the sphere spectrum, the C-motivic sphere spectrum, then the bigraded homotopy groups of C tau, it is this X. W T is okay. Yeah, so the bigraded homotopy groups of C tau can be calculated as this X. And I just want to remark here that this X is the E2 page of Adams-Novikov spectral sequence. I think I should write down the full name. Adams-Novikov spectral sequence. And actually, this is an observation by Isaacson that the tau Box-Stein spectral sequence, it has the same information as the Adams-Novikov spectral sequence, the classical Adams-Novikov spectral sequence. And the way they correspond to each other is that the E2 page of the Adams-Novikov, you start with the E2 page of the Adams-Novikov spectral sequence, and you attach everything with a polynomial generator tau, and that is the E1 page of the tau Box-Stein spectral sequence. And the differential here, dr from X to Y, correspond to a d2r plus 1 correspond to a dr x and kills tau to the power of ry. So, and there's also a way to translate from the tau Box-Stein spectral sequence to the Adams-Novikov spectral sequence. And well, the abstract I want to write down here is that this tells us that from the because the C or the cellular C motivic thing, it can be understood as a deformation of tau, and you use the tau box sign point of view to think about, to calculate the stable homotopy, the C motivic stable homotopy groups of the C motivic spectrum, then the calculation of that tau box sign spectral sequence actually is contained in the information in the tau box sign spectral sequence is contained in the Adams-Novikov spectral sequence, and that's classical. That is a classical spectral sequence, so it's classical information. So let me write this down. So from SH to understand SH of C, or more precisely cellular part, we can do it via the Adams-Novikov spectral sequence. And well, I think I'm and the second case, well, the second example we have is from the C2 equivariant to R motivic, and we have analogous of everything. We have analogy of everything here. That is, we have a theorem which tells us that a certain variation of the cellular R motivic category can be thought of the deformation of C motivic category. The C2 equivariant category. So theorem by Berkland, Hansinger. They say that the Artin-Tate R motivic category is a deformation of the C2 category. So everything is also P completed here with parameter ta. Okay. And the Artin-Tate here is some, it's a correct replacement for cellular in this case, because you want to include things like C2, the suspension spectrum of C2. And we can also use the Tab-Boxstein spectral sequence to calculate things. And in this case, Tab-Boxstein spectral sequence, it has the same information as what is called the C2 effective spectral sequence. Same information. And same information is it's basically the same meaning as what I wrote here. That is, you have the E2 page here, and then from there you can read of the E1 page here, and you have a differential here, and then you can transfer the differential, translate that differential to a differential in the Tab-Boxstein spectral sequence. And similarly, you can go from this side to this side. So there's some correspondence between the E1, E2 page and the differentials. Okay. And so in this case, we have, well, an analogous statement. Abstract is that if you start from the C2 equivariant category, then we can use the C2 effective spectral sequence to understand the Artin-Tate category, R motivic category. And if we can do some analogous thing to the C2 effective spectral sequence, then we can transform, if we can make an CP analogy of this thing, then we can translate the whole story to the CP equivariant case, and then we can build the question mark thing that we were thinking about at the beginning. But so that requires that we understand how CP equivariant C2 effective slice spectral sequence is constructed, and we can see if we can generalize that construction to the CP equivariant case. But the thing is that the C2 effective spectral sequence, its construction relies on the existence of R motivic category. So the construction of this thing is that you realize something called the R motivic slice spectral sequence. Or maybe more precisely, let me say the R motivic slice filtration. Therefore, it relies on the existence of the R motivic category. So this is bad because our goal is to build this R motivic category in the CP equivariant version of the R motivic category. But because this construction relies on the R motivic category, we cannot generalize this construction to the CP equivariant case. So we need to find another way to interpret the C2 effective slice spectral sequence. And let me state our theorem. Okay. With Gabe, Eva, and Mark. So we find a way to we construct constructed spectral sequence for general group CP. And we call it modified Adams-Novikov spectral sequence. So when P equals 2, this recovers the A-completed C2 effective slice spectral sequence up to some up to a décollage and regrading. So décollage here is some construction that allow you to shift pages. So E1 page of the C2 effective slice spectral sequence correspond to the E2 page of this modified Adams-Novikov spectral sequence. Okay, I have 5 minutes left, and maybe I can say a few words about the intuition or the construction of this modified Adams-Novikov spectral sequence. So intuition behind this is that how we think of this thing. Here in the Berkland-Hans-Singer's description, they think of the Artin Tate category as a deformation of one parameter deformation of C2. And in the C2 category, we have this important class A, so that another way to think about this Artin Tate category is that we can think of it as a two parameter deformation of the classical SH. So you think, well, let me see. The Artin Tate category as a two parameter deformation of SH. And then you have two parameters. You can run two types of Box-Stein spectral sequence, and you can swap the order you run them. So you can do A Box-Stein, then tau Box-Stein, or tau Box-Stein and A Box-Stein. Okay. And this is the target is the motivic sphere, amotivic sphere, and here it's CA smash theta adjoint and tau, and here you get theta and tau, and here you get CA join. And we have the square of things of for spectral sequences. And in fact, you can calculate all these things. Not this one, but you can calculate theta, calculate CA, calculate CA smash theta, their homotopy groups. And it turns out that you have different names. You have familiar names for these four legs. So this one collapse. And this one is the same information. I think we sort of mentioned it. This is the same information as a C2 ESS, C2 effective spectral sequence. This one is the same information. It's the same as a tau Box-Stein spectral sequence and the same information as the Adams-Novikov spectral sequence. And this one is A Box-Stein, but C2 equivariantly, A Box-Stein is the same as a homotopy fixed point spectral sequence. Okay, and if you look at this route, then that's something collapse plus a C2 effective spectral sequence. And if you look at this route, that's an Adams-Novikov spectral sequence plus a homotopy fixed point spectral sequence. And this route, they should give you same calculation. So that gives you intuitively, that gives you a way to think of the C2 effective spectral sequence as a combination of Adams-Novikov and homotopy fixed point spectral sequence. And the good thing about Adams-Novikov and homotopy fixed point spectral sequence is that you can easily generalize them to the CP equivariant case. And to deal with some convergence issue, we need to take a completion at these places. So this is a completed, and this is a completed. And that's why in our theorem, the statement is that, well, when P is 2, this recovers the A completed thing. And A completion is also what Borel means in the title of my talk. Okay. Yeah, I have I think I used up my time, and maybe the last thing I want to say is that though this is just it just gave you a completed part, where what we are trying to study right now is that how to go from the a completed part to the without a completion part. And the idea is, let me scroll it back. The idea is sort of already in this picture. So this is a completed picture. And from the a completed picture, you invert A, you get this Tate picture, the completed inverted picture. And then we're trying to go from here by some truncation to get here, and the pullback diagram information recovers this without a completion part. And this is the ongoing project with the same people, and we're trying to go in this direction. Okay, I think I stop here.
Sure. Let's thank Hana for the very interesting talk. Any questions?
I have a question. Can you hear me?
Yeah. Yeah.
So for example, in like so there are various spectra, like there's a C2 action on spectrum called TMF13, whose limit is TMF03, and there's a portion, like a cone inside that calculation, that's the final answer in positive degrees. Does this like effective spectral sequence have something to do with cutting off the information just in that positive cone, or?
Actually, I'm not very familiar with the TMF, but the calculation we're trying to run for a C3 example is the P equals to 3 case TMF, but I don't know the answer to the question that you just asked. Or maybe if you can explain the background to me in more details, I can say something. I'm not familiar with the stuff you mentioned.
I maybe another time.
Yeah.
You have time to explain the background of TMF right now.
Not right now.
Other questions? Yeah, if you want to ask a question of those who are online, just unmute yourself and ask a question.
Yeah, sorry.
I'm sorry, Hannah. I have a question.
Uh-huh.
So do you have sort of a candidate category in mind at this stage for what question mark is supposed to be? Or is that still to be determined based on the work that the work in progress so far?
So yeah, so if you allow a completion, then we have a construction of that question mark category. So basically it's so yeah, it uses a technique of synthetic spectrum or filter spectrum. You can build it using some thought of truncated co-simplicial thing. But that's only a completed version. And to get the without complete version is something that we are trying to achieve.
As a follow-up, could you maybe say a little bit more about how you get this from synthetic spectra? Is it like modules over some particular Adams tower, and which Adams tower?
Yeah. This is you can get it. So the filtered it is some module over filtered spectrum. Yeah, and that filter spectrum is related to this modified Adams Noikov spectral sequence.
Other questions? I have a question, Hannah. If your plan is to recover a mysterious stable homotopy, like motivic stable homotopy category from another stable homotopy category, or from this motivic CP stable homotopy category, then as a deformation, then how unique is this deformation? For instance, in those theorems that you quoted, that say that one motivic stable homotopy category is a deformation of another. How unique is this deformation? Because there might be various non-equivalent deformations in principle.
How unique? Oh, right. So, yeah, for example, in these two theorems, in the Gilgay-Wang-Shi theorem and the Berklan-Hansen-Singer theorem, I only state part of their result. So, for example, in the classical versus C-motivic case, this deformation has another property that if you take ta to be 0, so you look at the special fiber, then that is some algebraic category. Yeah, so if you take
Shouldn't it be the classical stable homotopic theory at tau equals 0 in the special fiber?
Let me write that down. If tau is 1, then this is SH. If tau is 0, then this is the BP2 star BP co-module. So you have the BP2 star BP co-module, that's an abelian category, and then you take Hovey's stable category of that. This is something algebraic. So the tau parameter tau, this deformation has this property. You can also identify special fiber and generic fiber. Co-module. And similarly, in the C2 equivariant versus R-motivic example, this is if ta is 1, then you get C2. If ta is 0, then you get also the stable category of, here you take BP star BP co-module, but BP star BP is the constant Mackey functor BP star BP. You take that abelian category and you take its corresponding stable category. And so its generic fiber, special fiber can also, both of them can be determined if you use this deformation.
Does it make the deformation theorem more unique in a way?
Yeah, I think so. This has an advantage that because the special fiber the generic fiber is a algebraic category, and in the algebraic category you can make calculation more accessible, and then you can translate the information, the calculational data you get in this algebraic category to the motivic category. So they have some strategy that doing calculation here and then translate the data you get to the R-motivic or C-motivic case.
So basically the hope is that you can get lots of properties and maybe recover the R-motivic stable homotopy category from the special fiber.
Yeah.
Thank you. Other questions? All right. Yeah, the time is up. So let's thank Hana for the very interesting talk. And if you want to send us a copy of those slides so that we can post them on our webpage, on the topology seminar webpage, we would be grateful. If you don't, just don't send them to us, but we will be happy to post them. And we'll also post the recorded session, the recorded talk, if you don't mind. We have a YouTube channel for the seminar.
Okay, yeah.
Sasha, I think Hana requested us not to put them here
I
too.
can't go to Piers tonight, so.
I'll take care of it, Hannah, don't worry.
Ayn, you're very quiet and hard to hear.
Together at 4:45.
Oh yeah, I think Sasha, did you receive an email? I think Hannah requested it.
Yeah, I reply but I will send